Okay, so let's go ahead and start. I know it's early, but I've got a lot of stuff that I want to cover. So we ended the last lecture talking about thermal relics, and the thing that we concluded with was this idea that if you have a perturbative coupling, the cross-section that you need is something like alpha squared over 200 GeV squared. And this is sort of the basic starting point for WIMP models. Now, I'm not going to spend too much time talking about WIMP models because there are plenty of opportunities to discuss them elsewhere, but it's still a good jumping off point. So if you ever have seen any talks about WIMPs at all, then you have seen this plot here, which is that you say that you have a thermal relic. A thermal relic in the early universe has a situation where dark matter comes in and annihilates into standard model stuff. And one of the most important aspects of dark matter in thinking about its formation is it gives you some clues of how to look for it. And one of the reasons why the WIMP has been such a popular model is because there are a lot of opportunities to look for it. And so the thing that you will hear is the following, that you draw this diagram where dark matter comes in and turns into standard model stuff, and then you say, well, I can draw that diagram. I can now consider this diagram in all sorts of different possible directions and think about the different signals. So I can consider the signal that we started off with, the direction this way, where time goes that way, where dark matter comes in and produces standard model, and that would be like cosmic ray signals, indirect detection signals. So in the halo of the galaxy or throughout the universe or in the early universe, dark matter annihilates, produces stuff, and then I see that stuff. I can consider time running this way, where dark matter comes in and hits a standard model particle and goes out, and that would be naturally interpreted as possibly a nuclear recoil or some deposition of energy of the dark matter into standard model particles. That's direct detection. Dark matter comes in, smacks something, and transfers some of its energy to us. Or I can run time this way, where standard model particles come in and I make dark matter, and that's what you would do at a collider. And this is sort of the make, break, or shake directions of looking for WIMPs. And this is a very nice plot, and it's very good for a colloquium. It's somewhere between PR and reality. It's not totally reliable because you never know what these final state particles are, so the idea that I can really do this rotation is not obvious, right? If you're at the LHC, then these particles better be gluons or quarks if you're going to make them, right? If you're doing a direct detection experiment, then likewise, this particle here better somehow be inside your nucleus, or whatever you're scattering off of. And if I'm doing indirect detection, then these particles better be something that I can observe, right? And so, and different models work better in different directions. So the idea that you can really just say, well, I've got these 3 different directions to look for them is true as sort of a jumping off point, but in particular, it's not anything like a robust, rotation of a diagram where you're really considering the different directions. The caveat to that is that there are specific models where, in fact, you really are rotating the diagram, and when you really are rotating the diagram, it becomes very, very powerful when you can, in those specific models, directly relate the annihilation cross-section to, say, a direct detection cross-section. So how do we think about these signals? Well, as I said before, your indirect detection signals, you have some thermal average, which is some expansion in velocity. And if this is a non-trivial piece, then you have a signal you can look for, but only then, because the universe has cooled down so much that this is significantly turned off. Direct detection signals, and I'm being very, very sketchy about this, in part because when Reuven comes, he will be talking about all sorts of different direct detection possibilities. Okay. But when you look at a direct detection possibility, what you're looking at is the possibility that dark matter comes in, has some mediator that for the moment I will just leave as a question mark, and then you have some nucleus that is scattered by the dark matter, and the energy is deposited into it. Now, dark matter, if it's a WIMP, has a mass of around 100 GeV, and the characteristic velocity is in the Milky Way is around 10 to the minus 3. So the characteristic energy that you're talking about depositing is up to about 100 keV. That's sort of the rough energy scale that you're talking about for these sorts of direct detection experiments. So there are two basic categories of direct detection. You have what's called spin independent and spin dependent. Spin dependent is a perfectly reasonable name. The idea is that this interaction here is somehow couples dark matter to the spin of your target. So only targets that have spin can have any sort of scattering. That's a perfectly reasonable name. Spin independent is a terrible, terrible, terrible name because it implies that it is simply something that it is not. And it's actually much more than that. And typically, in the spin-independent case, which is sort of the prototypical example of spin-independent would have been dark matter scattering via a Z boson. You end up with a cross-section which is proportional to the atomic number of the nucleus squared. So that is that you couple to some net charge of the nucleus, and you scatter off of that, and so it's enhanced because you're scattering off the nucleus coherently. And so spin independent, which you could think of as coherent scattering off of the whole nucleus, tends to have a much, much larger cross-section because of this A squared factor. And so almost all the plots that you see, not all, but almost all the plots you see are this type of scattering. So what does a direct detection plot look like? A direct detection plot typically has a shape that looks like this. I'm just going to explain what it is. On the x-axis, you have the dark matter mass, and on the y-axis, you have the cross-section per nucleon. So the way that you try and compare different experiments, because of course you might have one target that has germanium, another target that has xenon, and another target that has sodium, and you need to be able to compare these things. And so what you do is you calculate the scattering of dark matter off of a single nucleon, off of a single neutron or proton, and then you imagine what the total cross-section, you compare that to the experiment by scaling it up by the appropriate kinematical factors and A squared factors. So you calculate the scattering off of a single nucleus, you relate it to the scattering off of the nucleus in question, and that allows you to put all the different experiments on the same plot. To do that, then, you also have to make assumptions about what the distribution of velocities in the galaxy are, and what the local dark matter density is, and these sorts of things. These can matter in details and for specific cases. They tend not to matter sort of in the middles of these plots. So all plots have this basic shape, and there's a reason for this. We can understand the high mass region here, which is just to say that the number density of dark matter goes like the density of dark matter divided by the mass. So as you go to heavier and heavier masses, there are just fewer and fewer dark matter particles around. The relevant kinematical factor at high masses is the reduced mass of the dark matter nucleus system. So when you go to infinite dark matter mass, the kinematics of it are just dominated by the nucleus. So it's irrelevant what the dark matter mass is for very, very, very heavy dark matter. If you want, right, it doesn't matter if a nucleus is bouncing off of a bowling ball or if it's bouncing off of a freighter. It's bouncing off of something which is infinitely heavier than it. So at that point, nothing matters except for how many dark matter particles there are. So as you increase the mass, there are just fewer and fewer particles. So the limit gets weaker and weaker and weaker. And I should have said this is the excluded region. Okay. At low mass, what happens is that you have an actual physical detector. There's some energy threshold. You can't see signals that are below 2 keV or 3 keV or 10 keV or whatever your experimental threshold is. And so as the dark matter particle becomes lighter, eventually the characteristic energy that your dark matter is carrying is so low that it just doesn't actually get a signal into the detector. Now, it's not an abrupt cutoff. As you move to lighter and lighter particles, you start sampling the higher and higher velocity tail of the Maxwell-Boltzmann distribution, but it rapidly starts turning off, and there's some cutoff which is set by the escape velocity. So the Milky Way has some escape velocity, and we don't expect to have particles that have velocities higher than that around us. So once you get sufficiently low, there simply should be no dark matter particles that are capable of depositing energy in your experiment, and you lose sensitivity. So at low energies, your sensitivity goes to 0. At high masses, your sensitivity goes to 0, and somewhere in between, you have some best point, which usually tends to be in sort of like the 30 to 50 GeV range. These days, the best limits are coming from xenon experiments, xenon 100, xenon 1 ton, and Lux and Panda X. And the best limits are in the few times 10 to the minus 46 centimeters squared range of cross-section per nucleon. By comparison, the cross-section mediated by a Z boson is up here at about 10 to the minus 39 centimeters squared. So dark matter that scatters coherently off of a nuclei via a Z prime, which would have been your sort of most canonical conventional WIMP you could imagine, has been ruled out and was indeed ruled out when I started graduate school. So I'm not going to go into collider bands because you'll have individual lectures on that. Go to. Okay. So this is the WIMP. Now, from that jumping off point, I'd like to start discussing various other possibilities. Those other possibilities are going to be other production mechanisms and other thermal variants, but moving into the lighter mass regime. I'll go do the lighter mass regime last. And I'll do the other possibilities first. So the first possibility that I want to discuss in slightly more detail, and again, this is going to be better sketches than in the glossary, but not complete models. So let's consider a non-thermal model, but a very important one, or scenario, I should say. It's not a specific model, which is asymmetric dark matter. There's a very nice review by Catherine Zurich, where you can find a lot of this. So asymmetric dark matter, remember, is the idea that dark matter carries a fundamental asymmetry. There's more dark matter than anti-dark matter, or vice versa. And the most exciting models of this are the models where that asymmetry of dark matter is somehow connected to the fact that we have a baryon asymmetry in the universe. And so there's two basic approaches. There's something called a shared asymmetry. Which is, at least for our purposes, an unspecified origin. And then some process shares the dark matter number. And then there's a separate idea, which is cogenesis, which is where you have some process that generates dark matter and baryon number simultaneously. So the shared asymmetry would be you just have some mysterious source that creates some dark matter number, and then you have some higher dimension operators that share that number to the standard model, maybe through into leptons, and then you use phalerons to transmit the lepton number into the baryon number. Cogenesis, a sort of very simple example of cogenesis, is one that uses the neutrinos. So you imagine that you have a bunch of right-handed neutrinos. So this model looks a lot like leptogenesis. And they have interactions with the standard model Higgs and the standard model leptons. And then there's some additional interaction between that and some dark matter and some dark Higgs. Then you can calculate some asymmetry factor, which is the decay of n into chi phi minus the decay of n into chi bar phi bar divided by the total. And you can calculate the similar number for decays into leptons. Right, so this looks very much just like an ordinary leptogenesis model. You create some particle. It has a Majorana mass, so it doesn't have a well-defined, you violate your quantum number via its mass. You have some CP violation in these couplings that allows you to distinguish matter from antimatter. And then you have some out-of-equilibrium process, which is the decay of this particle. And the difference between this and a standard leptogenesis model is just that instead of only generating an asymmetry in leptons, this simultaneously decays and generates an asymmetry in the dark matter. So that would be an example of cogenesis. And you can calculate these things as you would in any leptogenesis model. Now, there's another possibility which has both physics and PR lessons within it, which there's a class of models that go by a bunch of names. One is Darko Genesis, but at basically the same time, you had people come up with names which were Hylogenesis and Exogenesis. And the only point that I make is these are all basically the same model, and I don't know if you've ever heard of any of them, but if I tell you Darko Genesis, you probably from the get-go are like, well, before I even tell you what I'm going to say, you kind of know what I'm talking about, right? Whereas if I tell you these things, you don't. So if anything sticks around, it's kind of this name. So just be aware of how clever you're trying to be when you name things. The idea there is that you have a dark sector, and you have your three conditions in the dark sector, right? So the conditions that you need to satisfy to generate an asymmetry, C p violation, C violation, quantum number violation, and out of equilibrium, you put that all into the dark sector. And then you have some operators, generally higher dimension operators, that transmit that number into the standard model. So for instance, you could write down an operator where if x is your dark matter, you could write down, for instance, x UDD in supersymmetry, some sort of superpotential operator like this. And that would then connect your dark matter number to baryon number. And so you generate the asymmetry over here, then some processes then transmit that number into the standard model. And in any given model, you can calculate what this rate is. These are very, very interesting models for a variety of reasons. One, because, as we said before, asymmetric models don't have the same annihilation signatures that symmetric models do. And also, this gives you a nice explanation for the origin of the baryon asymmetry. However, as I was also saying yesterday, there is this distinction between what is science and what is stuff that I tell my kids. And and these are beautiful models, but on the other hand, they're very, very hard to test because you've moved all the sort of interesting CP violation and quantum number violation into the dark sector. So you got to do all the hard work over in the dark sector, and then you transmit the results to the standard model. Doesn't mean it's wrong, it just means it's hard to test. Sorry? Well, this is not baryon number violating because this operator just tells you that X carries baryon number, right? So at that point, it's totally fine and you're not going to have any processes. You have to then go into the dark sector, find out about the X number violation here before you get anything. And at that point, you're starting to talk about much higher dimension operators and loops and things like this. And it becomes, and you can make it safe. You can make it safe. So that's all I want to say about asymmetric dark matter. So now I want to talk about thermal-ish models. So we described freeze out, so that was dark matter, which was in thermal equilibrium. Now we can talk about categories of models that are in equilibrium, but in sort of non-trivial ways or not quite in equilibrium. There's something that I don't think has a name that I know of. So I just refer to it as incomplete thermalization. And the idea there is that you have some process, some rate, that's going to allow your dark sector to be, your dark matter to be produced from interactions from the thermal bath. And it goes like some power, say t to the 5th over lambda to the 4th, just like in a conventional WIMP scenario. And as we know, that if you have something that goes like t to the 5th over lambda to the 4th, that this has a scaling that drops off more rapidly than the Hubble, which goes like t squared over m Planck. And so what we did in the context of WIMPs was we said, well, if you go to an early enough time, this process dominates, is larger than that, and thus the particle comes into thermal equilibrium. You wait, eventually it goes out of thermal equilibrium, and then that's what you're left with, and that was the idea of freeze out. But that assumed that we ever reached a point in the history of the universe where this actually was larger than that. When this was sort of a weak scale type cross-section, then that was great. But when this is something which is lower, it's not necessarily going to be, or when this cross-section is more suppressed, then this is not necessarily ever going to reach equilibrium. So in that case, you have a process where you have the thermal bath of the standard model producing this dark sector, but it never actually reaches equilibrium. So examples for this are the axino and the gravitino, at least in certain regions of parameter space. Gravitino. And the critical point about this is then that the number density of dark matter in this case is directly related to the reheating temperature of the universe, because pretty much your dominant production process is at the highest temperature that you start off with, right? After that, the annihilation rate, the production rate drops precipitously as the universe cools off. So however much of this stuff you make at the very, very beginning, okay? And after that, your production rate becomes less efficient. So these models that have this sort of non-thermal production through this non-thermal but incomplete thermalization process are hard to pin down because they're really dictated by this reheat temperature. So for some reheat temperatures, you have the right amount of dark matter. For some reheat temperatures, you have too much dark matter. And some reheat temperatures, you have too little dark matter. But this is one possibility of production. Next. Next is the possibility of something called freeze-in. So I don't know the first time that anybody talked about this. The first time that somebody coined this term that I know of was Hall, Yadamsik, March Russell and West. You can't read any of that, but that's why I said it out loud in 2009. This is called freeze-in. And the idea for freeze-in, well, again, keep in mind that for the freeze-out situation was something where you had an annihilation rate that was proportional to some high power of temperature, so it dropped faster than the Hubble rate. But if you have dimensionless couplings, that was, for instance, like WIMPs, where your cross-section was dominated by heavy mass-scale particles. But you can actually have situations where the annihilation is not suppressed by some dimension-full scale, but is in fact proportional to some dimension-less scale. In that case, your rate is proportional to those dimensionless quantities times t. So rather than having a process that becomes less and less important compared to the Hubble rate, this becomes more and more important compared to the Hubble rate as the universe drops. Because even though this rate is dropping, since the Hubble rate is dropping like t squared over m Planck, this is dropping more slowly, so its production process is actually dominated by whatever the last thing that happens for it is. And so some examples of this are, well, a good example for this is, for instance, a right-handed neutrino, or right-handed sneutrino with a Dirac mass. Because the Yukawa coupling gives you the dimensionless coupling. That allows you to produce this, but its dominant production comes late in the universe. The next thing that I want to discuss, and I think this is maybe something that gets a lot of interest these days, is 3-to-2 processes. So we assumed that dark matter was a 2-to-2 process, but you can have 3-to-2 processes for dark matter. So you can have something where 3 particles come in and 2 particles come out. Obviously, you can't have 5 fermions, but I'm just drawing these lines to be illustrative. In cases where you can have processes where this is dark matter and this is dark matter, where dark matter of 3 goes to dark matter of 2, and that's called cannibal dark matter, which is a separate situation from what I'm talking about here. I'm considering here 3-to-2 processes where 3 dark matter particles go into 2 standard model or other types of particles. So if you do this, you can go through basically the same exercise that we went through before. So you imagine you have some thermally average cross-section, which goes like some power, say alpha cubed, over mass scale to the 5th. Then you do exactly what we did before. You say that n squared sigma v is equal to the Hubble constant. That then tells you what the number density is at that time, where once again you assume that freeze-out happens sometime near when this particle goes non-relativistic. Yeah?
Possibly dumb question. So for this model to be viable, wouldn't that mean that the dark matter particle has to be like parity even?
So for this to be stable, you can have some sort of like Z3 type symmetry or something like this that allows you to have 3-to-2 type annihilation. So it's true that because I have an odd number of particles, this doesn't allow me to have just a straight up parity here, but you can have something that will keep it adequately stable. That's a good question. It's not a dumb question at all. What's that? So if I'm talking about the direct detection signals, then you'd be absolutely right, because the rate would be proportional to the amount of stuff that I have. But when you're calculating the equilibrium process, the way you should think about it is, I imagine that I'm a dark matter particle. I'm just going to be one of those things. And I want to know the probability for me to annihilate in the history of the universe. So what I'm really looking for in the 2-to-2 case is proportional to n, because I'm just asking what's the density of particles that I might run into. And here it's n squared because I'm asking what's the probability of me running into 2 particles at the same time. So So I'm just going to repeat that exercise that I did for the case of WIMPs. So n squared sigma v is T squared over m Planck. You imagine that the temperature of freeze out is approximately the mass of the particle in question, which I'm assuming here is the same as the mass scale that's setting the cross-section, which needn't be the case. But for simplicity, that's what we're assuming. And then I asked the question about rho. So rho, which is m times n, which then goes like m to the 9 halves over alpha to the 3 halves m Planck to the 1 half. And then I do what I did before, which is I redshift it from then until now. So I take T matter radiation equality over m cubed times this number. And I set that equal to the energy density in photons at matter radiation equality. Remember, the energy density in photons is just T to the 4th. At matter radiation equality, this is what the dark matter energy density is going to be. This is what the photon energy density is going to be. I set them equal. I do some algebra. And when you do some algebra, you get that m is, 2/3 m Planck, 1/3. So before, for the WIMP miracle, we found that the characteristic mass scale was the geometric mean of matter radiation equality and m Planck. For a 3-to-2 process, you get that the mass is the T to the 2/3 m Planck to the 1/3. So if you set alpha equal to 1, imagine it's a strongly interacting particle, then you get m is just equal to this, which is around 100 MeV. Okay. And so people like to call this the SIMP miracle, or strongly interacting massive particle miracle. This 100 MeV is, of course, very similar to the scale of strong interactions in the standard model, but that doesn't necessarily mean that you're literally talking about this thing having standard model strong interactions, and indeed such models are very hard to build. But it does tell you that a particle that has a characteristic mass scale like this, that annihilates through 3-to-2 processes like that, very naturally can give you the right relic abundance.
I might have missed it before, but the matter radiation equality, why is that a relevant temperature?
Oh, it's a relevant temperature in the sense that it allows me to, at some point in this calculation, you want to say that I calculate the amount of dark matter in the early universe, and I want to match that to the amount of dark matter that I see in the current universe. One way to do that would be to redshift it from when it formed to now, and then just compare it to now. But another way to do it is to say, well, at matter radiation equality, I know how much dark matter there was then. It was the same amount as there was in photons. So all I'm doing is, instead of saying I'm going to compare the amount of dark matter that was produced to the amount of dark matter now, I'm saying I'm going to find the amount of dark matter that was produced and compare it to the amount at matter radiation equality. Same basic concept. It's just normalizing it to a number that I know in our existing universe. And I know that at the matter radiation equality, the dark matter energy density is the same as the photon energy density, and the photon energy density is just T to the 4th. So this is just a simple way of trying to match the calculation onto the observed universe in a way that doesn't have to meet, because we're kind of at an ad hoc time right now. So you have to put in all sorts of random factors. This makes it very nice and clean. Also, T matter radiation equality is an EV, so it makes my math very simple. Yeah?
So for the SIM miracle that is published by like Gary, Yoni, and Hiroshi, I think it's 3 dark matter to 2 dark matter.
Was it 3 dark matter to 2 dark matter? You have to be a little careful with that particular model, though, because it's cannibal.
But at least that paper with the title SIM miracle, it is 3 dark matter to 2 dark matter.
Thank you. So this is, remember, an interesting scale because this particular scale is one where you have naturally scattering processes that can be relevant for, if you have an annihilation cross-section which is like this, you also can expect to have scattering cross-sections which are characterized by the same scale. And if so, we know that this scale, remember, is roughly equal to 1 centimeter squared per gram, which is the relevant scale that you need to do things like change your galaxy cores and address the too big to fail problem and things like that. So this is a very interesting scale because of that. Other people would say that the beryllium excess, pointing to something around 17 MeV, also is sort of pointing to the same energy scale. So possibly there's something to that. Next. Yep. How do I what? Well, this is the dark matter annihilation process, so it's not necessarily alpha of its coupling to us. So I can imagine that this is, for instance, freezing out into, say, an unstable particle in its own sector. We'll discuss more models like this in a second. So next, you have forbidden dark matter. Which was discussed in the context of, I believe, SUSY-type models back in '91, and more recently by D'Angelo and Ruderman. Who kind of understood it in sort of a modern and proper context. And so the idea is there that we always assumed that dark matter was annihilating into standard model particles. So let me call this dark matter and dark matter. And let me call this X and X, which is some standard model particle. Or it could be a non-standard model particle that then itself is in thermal equilibrium with the standard model particle, but something. This X is what's going to be maintaining the equilibrium. And usually we assume that dark matter is annihilating into something lighter than it. So for instance, dark matter is annihilating to WW. Dark matter is a TeV, W is 81 GeV, whatever. Or that it's annihilating to Higgs bosons or something like that. The idea here is that the mass of this final state could actually be larger than the mass of the initial state. And in that case, the cross-section estimate that you do, which is alpha dark squared divided by m dark matter squared, comes with an additional suppression of 2 delta m over t, which is just to say that I need to find 2 dark matter particles that have enough kinetic energy in them to overcome the fact that they kinematically cannot actually annihilate, right? So I go out on the tail of my Boltzmann distribution. If I go out on the tail of my Boltzmann distribution, I find these particles that have enough energy to annihilate, and then I mediate my annihilation process from that tail. If you do that, you can now consider much, much larger coupling constants because you're sort of compensating for it by this exponential suppression. And you can write an overall plot where you have some coupling constant here, and you have, say, mass down here. This is KeV, and this is, say, PeV. And so up here, you hit the unitarity bound. Along here, you have a nice thermal dark matter particle. So if your cross-section goes like alpha squared over m chi squared, then you can dial down your dark matter mass and your coupling constant at the same time. Up here, you have WIMPs. Here you have ultra-weakly coupled dark matter. Then up here, you have forbidden dark matter. And sort of around here, you have SIMP dark matter, strongly interacting massive particle dark matter. So that sort of fills out the, at least in some dimensions, the sort of coupling constant mass range of the types of dark matter you have. There's a thermal band. This is all thermal. You have a region here where it's just standard 2 to 2 annihilation. Coupling constants are perturbative. Mass scales are a weak scale. You can go above that or below that by going to stronger couplings or weaker couplings and lighter masses. At some point, you have too strong of couplings, and you hit the unitarity bound. And then in this region, you can still get dark matter, but the only way you can get dark matter is if you kinematically suppress its annihilation, or you do something like 3-2 processes. Yes, that's 4 pi. Alpha is a characteristic interaction strength. Yeah. Yeah.
So if X are heavier than dark matter, what stops X is depopulating dark matter?
From depopulating dark matter?
Actually, just depopulating dark matter.
Oh, you mean like just the reverse process? Well, the idea would be that X has to be somehow unstable, and it decays dominantly into other things.
Oh, I see.
That would be the easiest way to do this. So let's see. It's now, I start at 9:15, and I'm allowed to go until 10:45. Okay. So I'm going to come back to thermal models in a second when I come to portal models. I want to talk about one slightly different production mechanism, which is relevant for the axion, but what I'm going to write down right now is not literally the axion, so I'm going to put it in quotes, but it'll be relevant for stuff that Michael's talking about. And it's relevant not just for the axion, it's relevant for any type of coherently oscillating scalar fields for dark matter. So if you write the Klein-Gordon equation for a scalar field in an expanding universe, then it's the ordinary Klein-Gordon equation with this additional drag term. And so you can do a very simple exercise and imagine that you're living actually in de Sitter space, just to simplify calculations. So imagine that this Hubble constant is just constant. And then you can try solving this by putting in an oscillating scalar field. When you put in this, I'm using a real phase right here, or sorry, real phase, real frequency. Then you can solve for the frequency. And when you do that, you all know how to do the quadratic formula, and yet I will write it nonetheless. So here's what you find. So the frequency is this. So you can take two limiting cases. You can take first that m is much, much less than Hubble. Now remember we said if m is much, much less than Hubble, then that means that effectively the particle is massless. And then the two solutions you get are these. So if you take Hubble to be constant, then you can imagine considering the mode, you can consider this mode first. So imagine what kind of energy density that has. Well, the energy density would be proportional to, say, m squared phi squared, which is like m squared phi naught squared. But since W is minus 3h, then that tells me that this field then is going to, scale like e to the minus, since A is proportional to e to the ht in de Sitter space, and this is now going to go like e to the 3ht, phi squared goes like e to the minus 6ht, which tells me that this energy density goes like m squared phi naught squared a to the minus 6. Okay. So if I consider this mode, the energy density in that mode damps off extremely rapidly. On the other hand, I can put in this mode here, and what do I get? I get m squared phi naught squared e to the minus 4 m squared over 3ht, which is like m squared phi naught squared times a to the minus 4 m squared, sorry, m over 3 h squared, m squared over h t. If I plug in t, which is comparable to the Hubble time, then this is a to the minus 4m squared over 3h squared. But by definition, we are taking the case where m was much, much less than Hubble. Since m is much, much less than Hubble, in one Hubble time, this coefficient here is very, very small, which tells me that the energy density in this scalar field is barely changing. This regime is probably well known to many of you. This is the slow roll regime of the scalar field, which is just to say that if I have a scalar field whose mass is much, much less than the Hubble constant, then it effectively is massless, and even though in the early universe you would expect it to drive down towards 0, it doesn't. It more or less sits there and drags very, 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 very slowly. If you consider the opposite limit, where m is larger than the Hubble constant, then you have frequencies that go like that. So you have both a real and an imaginary part to it. In that case, phi will evolve with some decay term and some oscillating term. And of course, this oscillating term is the usual piece for a Klein-Gordon field, which is just something oscillating in its space. And if you look at how the energy density of this field goes, well, as we said before, so if phi is going like e to the minus 3ht over 2, but this is de Sitter space, so the Hubble constant is just going like e to, or sorry, the scale factor is going like e to the ht, then this is telling me that phi is going like a to the minus 3/2. So the energy density in this field, which is approximately m squared phi squared, is going like a to the minus 3. And this is the important result. If I have a scalar field whose mass is larger than the Hubble scale, and I allow it to oscillate freely in the universe, the energy density in that scalar field will decay off like a to the minus 3. But remember that a particle has a decay which is related to its equation of state parameter, and if you fall off like a to the minus 3, that means that you have pressureless matter. So this type of matter here is effectively diluting like cold dark matter. So this is a way of generating non-thermal dark matter. You start with dark matter, which for whatever reason, in this case it's slow roll, but it doesn't have to be slow roll. You start with dark matter at some initial condition energy that's up on its potential. For whatever reason, possibly because of a thermal phase transition, possibly because of just this effect, it starts oscillating. Once it starts oscillating, it gradually will decay away, and this energy density will die off like a to the minus 3, and this will act like dark matter. Now, the axion is not literally that, because it doesn't go from this slow roll to non-slow roll. You have a QCD phase transition. But much of the dynamics can be understood from just a oscillating scalar field. Questions about that?
So you said V is rho.
Sorry?
V is the energy density.
Well, properly, the energy density is m squared phi squared plus phi dot squared over 2, or phi dot squared, right?
I was trying to make that a to the minus 4, because that's what it should be for radiation, right? And in the limit m much smaller than
But this is not, that's the point. This is not, even though m is very, very small, this is a non-thermal process. So this particle doesn't have kinetic energy that's set by T. That's the interesting thing about this. This is a very, very light particle, but it's sitting there doing nothing, starts coherently oscillating, and when it starts coherently oscillating, you can calculate what kind of dilution it has, and it actually dilutes like dark matter, not like radiation, even though it's very light. But it doesn't have a thermal distribution.
So then in this case, correct Rayleigh density is obtained by basic initial conditions?
It's obtained by a combination, in any given model it'll be different. It'll be obtained by a combination of initial conditions, when the oscillation starts, which can be dependent on the parameters of the model. So it could be the initial value of the field combined with when it starts oscillating.
But one way or the other, ignoring all possible interactions with a given lighter particle.
What do you mean?
Because we are just calculating energy density, ignoring any other possible either hyperlation or elimination of such particle.
That's right. I'm assuming that there's no decay of this particle into ordinary. I'm assuming that its evolution is straightforward like this. That's right. So all other processes should be much longer than Hubble.
Small question. If n is way larger than Hubble, then what are the footprints this kind of oscillation will lead to?
So there are a lot of really interesting ones. So I don't know how much Michael's going to talk about this, but I know Peter Graham next week is going to be talking a lot about the signals of oscillating scalar fields and their experimental consequences, because there's been a huge experimental effort by a number of people, including Peter especially. So you will hear a lot about that. Okay. Good. So let me now consider more or less more exotic models. Okay? So up to this point, thinking about the thermal models, we're really thinking about models where we are either totally unspecifying what the process was by which dark matter annihilates into the standard model, or you're talking about a WIMP with a capital W, where you mean literally that this thing interacts with W bosons and Z bosons and things like that. Now I'd like to change gears and start talking about other ways that dark matter can interact with the standard model and thus have both signals in direct, indirect, collider, or produce it thermally in the early universe. So let me start by talking about effective Z-prime models. These are, by and large, just WIMP models, but with some additional knobs. So if you imagine that in your universe you have some additional U1 gauge boson, which is Higgsed at a scale b sub x. And you can imagine that you have dark matter couples to this Z prime. Then you can ask the question, how is that particle going to interact with the standard model? Well, if that scale Vx is above the weak scale, then you actually have a lot of freedom, because that is a Higgs Z prime, which means that it can more or less, from the effective theory point of view, have whatever interactions you want it to have with standard model fermions. Let me give you an example of how this works. So you imagine in the standard model you have your chiral fermions, QU DLE, and then you imagine that you have some dark sector, not necessarily dark sector, but partner fermions that I'm going to write with capital, and their vector conjugates. So Q is a 3 under SU3 and a 2 under SU2 with hypercharge a sixth. Q conjugate is a 3 bar with hypercharge minus a sixth. But then I also assume that under this U1x, these guys have +1, and these guys have -1. Now, in any real model, you don't need all these things. You just need one pair of these things. And the reason why you do it like this is so that anomalies cancel trivially. So imagine that you have some Higgs boson that acquires a VEV, V sub x. Then you can write down the following terms. You write down lambda phi, for instance, u conjugate. Okay? So when V sub x gets a VEV, this is going to give a Dirac mass between the standard model up quark and this right-handed up quark. But you also write down some mass, which is a bit larger than V sub x, between u and u conjugate. Well, if you do this, what happens is that u tries to marry u conjugate, and capital U tries to marry u conjugate, but you have two, if you want to say, left-handed fields and only one right-handed field, which means that this u conjugate can only marry one linear combination of little u and big U. So one linear combination is massive, and one linear combination is massless. So you end up with some light u, which is some mixing angle of u and some mixing angle of u. Right? And this light up quark is the thing that we then call the up quark, because it's the massless degree of freedom that picks up its mass at the end of the day via Yukawa couplings with the Higgs boson. Right? But this up quark is secretly containing a portion of some field that carried an additional gauge interaction, and thus this residual up quark then carries that effective interaction. And so this is what you would refer to as an effective Z prime, because it's an effective interaction. There's no point in the theory where the degrees of freedom that we are have gauge couplings. They're just effective operators in the low energy. But as a consequence, you can now have situations where dark matter then annihilates to these things. So dark matter can go through this Z prime into standard model fermions at a low energy scale, where this coupling constant here is just g sine squared theta. Okay. And since you know that these sorts of things have the expected coupling constant that you need to get the right relic abundance is something like a coupling constant of a 30th and a mass scale of a TeV, even with a mixing angle which is relatively small, you can still achieve this sort of a model. Yeah? Well, since they carry these U1x charges, that forbids these interactions, because the standard model is neutral under U1x. These things carry the U1x charges, so they can only get mass terms with each other. So the only kind of mass term you can get with the standard model is once that U1x is broken. And the reason I point this out, this kind of model out, is just to emphasize that once you go below the scale of the Z prime, you know, people talk about B minus L models, people talk about hypercharged-like models, kinetic mixing models, but as long as you're below the scale of the Z prime, you can really have any couplings you want. That F can be leptons, it can be up quarks, it can be bottom quarks. You have to worry about flavor changing neutral currents and all these things, but a priori, from a theoretical point of view, you can do whatever you want. Now, this is very much just a conventional WIMP, though, with just some fancy couplings, because experimentally we know that those quarks and leptons have to be very heavy. Otherwise, we would have seen them at colliders. Okay. Next. So a lot of attention these days has gone into discussions of what are called portal models. So these have gotten a lot of attention, in part because as we've done a lot of WIMP searches and as we've done collider searches and not found anything, people have started stepping back and saying, okay, more generally, how are we going to have dark matter that talks to us? And so the idea is that you have your dark sector, and you have your standard model, and then there's some sort of operator that connects these two sectors. And any operator that you write down that has standard model on one side and dark sector on the other side would be a portal. But for a variety of reasons, people are, of course, interested in the lowest dimension operators that can do this. And so that leads us to 3.5 portals. So I will write down those portals. Those portals are the Higgs portal, the neutrino portal, and the gauge or kinetic mixing portal. So this is the neutrino portal. This is the gauge or kinetic mixing portal. And this is the Higgs portal. There are obviously two operators here that I've written down, and I've categorized them as the Higgs portal. There's the renormalizable Higgs portal, which is dimension 4. So phi here would be your dark sector particle, phi dagger phi. The Higgs would be the Higgs, phi h dagger h. But you can also, if that phi is a singlet, you can write down a super renormalizable operator, a phi h dagger. That also gives you a connection between a dark sector particle and the Higgs. In that case, of course, phi is not the dark matter, but it can be part of the dark sector. And you can actually usually achieve this operator trivially by taking this operator and giving a vev to phi, obviously. So there's two different scenarios that people typically talk about for thermal models via portals. You have hidden sector annihilation, and you have direct annihilation. So hidden sector annihilation would be something like dark matter annihilating into phi particles where those phi particles are part of the dark sector, and then phi maintains equilibrium through some other process, or it's unstable. Direct annihilation is something where you have some process by which, say, the standard model or dark matter annihilates directly into the standard model. And these are qualitatively very different in their signatures and types of things that you get out of it. So let me start with the Higgs portal. Now there are all sorts of twists and turns and variants that you can do on these sorts of models. The most important thing to keep in mind is that, at least for the Higgs portal, that the Higgs boson itself has very, very small couplings to fermions. So if you want to get into sort of a light dark matter model, the Higgs portal oftentimes is not the one that you use because its couplings to light particles are so suppressed. There's a classic paper on the Higgs portal by Burgess, Pospelov, and Feldwy. So you can look at that and references there too. And the idea of the Higgs portal and how you can do dark matter with it is you can just imagine that this phi particle is your dark matter, and you have a process where you can have annihilations like this, or you can have annihilations, once the Higgs gets a vev, through an s channel into gauge bosons or fermions. And obviously, depending on the mass of the phi, the coupling constant that you need here, lambda, varies, but lambda is typically of the order of 10 to the minus 2, an isoperturbative coupling for a weak scale particle phi. For lighter phis, as phi gets down to sort of like 20, 10 GeV, because the annihilation goes through the Higgs, the coupling constants that you need rise rapidly. And as a consequence, there is a direct detection signal where phi can exchange a Higgs boson and scatter off of a nucleus. For in the sort of 60 GeV range with this sort of a coupling constant, this direct detection cross-section is around 10 to the minus 45 centimeters squared. So over a lot of the parameter space, this model, as it's written, is excluded by direct detection. There's a specific region right around 60 GeV where you go through a resonance, where the coupling constant here can be very small, and there the direct detection cross-sections can be smaller, and this can be safe. But over a lot of the parameter space, this model currently is excluded by recent direct detection experiments. Or you can go to higher masses. Which Yukawas? Here? So the interaction of the Higgs boson to protons and neutrons is a deep and important subject because there's contributions to the coupling constant of the Higgs through its interactions with up quarks, down quarks, strange quarks, because even though there's very little strange quark content in terms of number, it's got a bigger coupling to the Higgs, and also through its coupling to the gluon field strength, because as you wiggle the Higgs mass, then you're changing the mass of the top quark, and thus you're changing alpha strong. And all these things are contributing. Overall, the coupling constant of the Higgs to nucleons is about a factor of a few down from m proton over v. So it's about 10 to the minus 3, the effective one. Sorry? You haven't measured these, but that's actually not that's not the dominant uncertainty. The dominant uncertainty for this, I believe, at the state of the art, was the strange quark content. I don't think that it's if you change the up quark Yukawa coupling by a factor of 2, you're not going to change this by that much. So the Higgs portal is a very, very nice portal, but at least as you write it down like this is still something that looks very much like an ordinary WIMP. The mass scale that's relevant is still sort of in the 100 GeV range. Its annihilation is into either Higgs bosons or into standard model fermions or gauge bosons. So it still looks very, very WIMP-like, even though it's a portal model. There is a variant where you go through a hidden sector annihilation, where dark matter annihilates into phi, and then phi decays into standard model things that looks different, but I'll discuss that better in the context of the kinetic mixing models. So the next portal that I want to discuss is the kinetic mixing portal. This is the one that's gotten by far the most attention of late, and it's very well studied at this point, and there are a lot of interesting experimental efforts that are underway, and Reuven will talk about them. Usually, the normalization of the term that you write down in your Lagrangian is epsilon over 2 cosine theta weak. The reason for that is that people are usually, so B mu nu is of course hypercharged, and the F mu nu here is the U1 for the dark sector. So there's some dark sector U1. You imagine that it's Higgsed by some dark Higgs at some scale. Most often people are interested in these scenarios where that Higgsing scale is sort of in the many GeV to MEV or lighter regime. At least that's sort of what people are interested in right now. And as a consequence, you're at a scale below electroweak symmetry breaking, so you're most interested in actually mixing F dark with F E and M. So that's what this cosine theta cancels off. So when you replace this B mu nu by F mu nu E and M, it looks just like epsilon over 2. And so this normalization means that at the end of the day, you have some kinetic mixing matrix between your dark U1 and, at the end of the day, E and M. And when you diagonalize that, you end up where the standard model fermions couple to the dark photon with something which is proportional to their electric charge, the electric coupling constant, their electric charge, whatever it is, 1, 2/3, 1/3, and epsilon, this small parameter here, which is typically something like 10 to the minus 3 or smaller. There's an important aside that I want to make about this particular model that can often be a confusion, which is that we always end up picking a basis for discussing these types of models where we say there's a dark photon and then there's the ordinary photon, and we say that the standard model talks to the dark photon with this coupling, and we never say that the dark matter talks to the ordinary photon with a small coupling. And there's a reason for that, and that is that you have a dark Higgs, phi, and you have your dark matter chi, and the assumption is that they start off charged under the same U1. When you diagonalize your kinetic mixing matrix, they are still talking to the same U1, so when phi gets a VEV, it gives a VEV to one linear combination of these vector bosons. That massive linear combination is precisely the same linear combination that dark matter talks to. Therefore, the thing that this gives a mass to is the same thing that this thing talks to, which means that dark matter only talks to the massive gauge boson. Okay? If you wanted to have dark matter be millicharged, you would need to have had its U1 charges initially misaligned with that, which is to say that you effectively would have had to have given dark matter a tiny, tiny millicharge to begin with if you wanted to have a tiny, tiny millicharge to end up with. If it starts off with the same charge, or at least its charges are aligned with the phi, then when phi gives a mass to a linear combination, and that's the one that this talks to, and it only talks to the massive component. In contrast, standard model fermions, which talk to B mu nu or F mu nu electromagnetism, what we define by the photon is we mean the massless degree of freedom, right? That's what we define to be the photon, not the linear combination that talks to standard model particles. So the linear combination that talks to standard model particles is some combination of the massless state and the massive state, and thus all ordinary particles have their usual charges and interactions with the massless gauge boson, but they have an epsilon interaction with the dark photon. That's a long way of going through this story, except to say that basically most of the time we're talking about a situation where you have a standard model, you have a dark photon, and you have a dark Higgs, and you have dark matter, and the effect is that that dark photon talks to standard model particles proportional to their charge. So these models have two scenarios. They have the hidden sector annihilation and the direct annihilation. So a hidden sector annihilation looks like this. Equilibrium in these models is usually maintained through a process that looks like Compton scattering. So an electron comes in, couples to a dark photon with a suppression epsilon, then emits an ordinary photon, or vice versa. So this is usually the equilibrium process for the two thermal baths, so what keeps our bath and the dark bath in thermal equilibrium, and dark matter annihilates directly into gamma dark. In this case, the cross-section for annihilation just goes like alpha dark squared over m dark matter squared, which it looks just like an ordinary WIMP cross-section. So to the extent that this doesn't look like a WIMP, it's because you make alpha dark very, very small, which you can do. You can just dial down alpha dark and dial down the mass, and you can make this thing as light as you want. But there's nothing fundamentally about such a model that wants it to be light dark matter. If anything, a model like this wants to be sort of more in the weak scale. In contrast, direct annihilation is more situated for being light dark matter. So I think the first people to really look at these types of models were Bohm and Fayet. And so there, if dark matter is charged under this U1, and you're directly annihilating into standard model fermions, then parametrically, this cross-section now goes like alpha dark from the dark matter interaction, alpha standard model from this interaction, so alpha electromagnetic generally. Epsilon squared, that goes because the coupling constant of standard model fermions is proportional to epsilon. And then, since we're assuming that that process doesn't happen, these dark matter particles have to be lighter than the dark photon. So this whole thing then goes like m dark matter over m dark photon to the fourth. Now, typically you assume that these things have roughly the same mass scale. So this whole cross-section then is going like coupling constants, small number, divided by dark sector scale. That's sort of the rough scaling of this thing. Now we know that if alpha is sort of typically perturbative, that we would like the denominator, if you forget about that, we would like the denominator to be roughly TeV. But this interaction comes with this additional epsilon, which we know from all sorts of experiments has to be something like 10 to the minus 3 or so. That tells you then that this mass must also be smaller by 10 to the 3 or so. So it's very natural to imagine that you're in situations where this dark matter would be very light, 10 GeV, 1 GeV, 100 MeV, and so on. And so that's a lot of the discussion. And that's kind of what makes this interesting. Ordinarily, if you have a perturbative annihilation cross-section that just goes like alpha squared over 10 GeV or 1 GeV, that is way too big of a cross-section, and that dark matter will deplete itself down and won't be the dark matter. Such dark matter, as we discussed, has problems with the CMB in that it naturally annihilates into electrons, muons, things that give interactions and deposit energy into the CMB. It also has problems with direct detection if it's kinematically accessible. So you can calculate the cross-section per nucleon, and you can pick some characteristic numbers. So if you have an interaction where dark matter scatters through this dark photon off of ordinary matter, remember that this couples to charge, so it will couple to a proton with coupling constant 1 times epsilon. And so the cross-section per nucleon, you can plug in your favorite nucleon. This is set up for germanium. With a coupling, with a mixing of 10 to the minus 3, and alpha dark, which is comparable to the electromagnetic fine structure constant, a dark photon, which is a GeV, you get a direct detection cross-section, which is 10 to the minus 37 centimeters squared. The Z, remember, gives you 10 to the minus 39 centimeters squared. So this is a huge cross-section. Current limits are down to 10 to the minus 45 and better centimeters squared. So if this dark matter, if you have a dark matter particle interacting via a dark photon like this, you need to do one of two things. You either need to turn off this direct detection cross-section, or you need to move this thing down into the light mass regime. Okay? one way to turn off the direct detection cross-section is to do the splitting effect that takes care of the CMB. So if you imagine that your dark matter is split into chi2 and chi1, then your vector interaction is now off diagonal. And so if it's kinematically impossible for dark matter to scatter into the excited state, you can turn this off. And when you do that, you also turn off the CMB annihilation. So it's not impossible to save these models, but naively, they have very, very big CMB signals, and they have very, very big direct detection signals unless they get light enough. These models feature a couple of interesting signatures, if you're talking about light dark matter or not. If the mediator is lighter than the dark matter, then you can have a phenomenon which is known as the Sommerfeld enhancement, which is pretty commonly understood now. The idea of the Sommerfeld enhancement, which is known to all nuclear physicists and recently particle physicists, is that if you have a long-range interaction between dark matter, ordinarily we calculate the perturbative cross-section of chi going into whatever. But if there's a long-range interaction as these particles come near each other, that attractive interaction can essentially pull the dark matter particles together and boost their annihilation cross-section. The analogy is if you take the Earth and you throw a rock at it, the cross-section is pi r squared. But if you throw the rock very slowly, there will be a gravitational focusing effect that will lead to an enhancement. Something like that. And this is the analogy for dark matter. You throw the dark matter particles at each other, they attract each other, and you get an enhancement of the cross-section. That can be very relevant for direct detection signals, if you have them. The other interesting signature, which is sort of new for these types of models, is the fact that you now have this dark photon. And if it's sort of in the GeV mass range, you can look for it at a variety of experiments. Reuven's going to talk about all sorts of new experiments that are going on, so I'll just mention one thing, which is that if you have some process at a collider that produces the dark photon, so you have some process, PP, goes to something that then spits out a dark photon, that dark photon will be very boosted. It'll typically have energies which are comparable to the energies of the system. So when it decays to pairs of leptons that are highly collimated. Most LHC analyses, most high-energy collider analyses look for isolated leptons, not collimated leptons like this. So this object has been termed a lepton jet. Not just two leptons. Sometimes you have more leptons than just two. But the idea is that if you have a highly boosted object that decays into leptons, it looks like a jet because the total invariant mass of the system is just like a GeV, but it's got a high lepton content. And so that's a signature of these types of models. And Reuven will talk about all sorts of decays. Now that's under the assumption that dark matter carries the U1 charge and annihilates thermally. There's an alternative possibility, which is that the dark photon itself could be dark matter. If the dark photon is heavier than electrons, then it will decay very promptly into electrons. But if it's lighter than electrons, then all it can decay into is 3 photons. And that process is very, very suppressed. So it can very easily live the age of the universe once it gets down below the mass of the electron. So the question is then how you make such dark matter. Most processes that people thought about originally were not sufficient. But it was pointed out by, I don't have it on this piece of paper. Maybe I have it on this piece of paper. I think it was Graham, Rajendran, and Martin. Where did I write that formula? I don't have the number written down. But the expression that you get is something like omega dark matter can be something like the omega of the dark photon can be something like what you want times, make sure I get the scaling right, m over 10 to the minus 5 eV, I think, times h over 10 to the 14 GeV. I think I'm getting the power counting right. The idea that was pointed out by Martin, Rajendran, and Graham was that inflationary perturbations naturally generate any approximately massless modes in the early universe. So during inflation, you should produce these things, and you can ask how much of that stuff should be around to give the right dark matter. And if you take a Hubble constant, which is 10 to the 14 GeV, you can have a 10 to the minus 5 mass dark matter, dark photon. And as you lower the Hubble constant, you can raise the mass of the dark photon. This model is interesting in part because it has a very special feature which is different from a lot of dark matter models, which is that you can look for this through absorptive processes. This dark matter is stable not because of some symmetry or something like that, but just because it's too long-lived. But it can actually come into your experiment and be absorbed and produce some energy just by the fact that it has rest mass. So it's a very interesting particle to look for. How heavy or what? Oh, you can start it around here, and you can go up to about keV. You just need to lower your Hubble scale during inflation. Sorry, I should have said this is the Hubble constant during inflation. So if you have very high scale inflation, then you make a different amount than if you have low scale inflation because the fluctuations are just smaller when you have lower scale inflation. This is not a thermal model. This is a non-thermal production process. You're imagining that your coupling constant epsilon is sufficiently small that this thing stays out of thermal equilibrium. You produce it through these primordial fluctuations, and then it. And that's how it evades an effect. Right. This is not. Yeah. This is not a. This is cold dark matter all the way down. The last portal, I don't have to talk too much about because Andre will talk about everything. Right, Andre? Thank you. The neutrino portal is just a Yukawa coupling between the standard model left-handed leptons and some sterile neutrino n. As I said before, this n does not have to be the gut right-handed neutrino. It's just any sterile neutrino. Any sterile neutrino is quite happy to marry off against this. If all I write down is this, then I get a Dirac mass. If I add a Majorana mass, then I have a seesaw. Which is nice, of course, because it can give me neutrino masses. But you can also imagine that this n talks to some bigger dark sector. So if you integrate it out, you can write down LH times O dark sector divided by the mass of the sterile neutrino to some power. And that can lead to new sorts of models. And actually, at the moment, that's the kind of thing that, one of the things that I'm interested in. But I'm not going to talk much about any of that because Andre's here and he can talk about everything about neutrinos. And also, I'm out of time. So I'm going to stop. Before I stop, I'm going to say one thing, because this has all been physics. And now I'm going to say something which is not physics, because we can learn those things too. And it is that I'm not super old yet, but I'm old enough that I've seen some changes in the field. And so I don't know how many of you are going to work on dark matter or not. I'm just talking about dark matter. Many of you might. But the thing that I'll say is that when I started working on dark matter, and I started writing down models, everybody was like, that is a crazy model. That is a weird model. That's a kludgy model. People said all sorts of not very nice things about a lot of the models I worked on. But then over time, people got used to them. And now people don't say those things anymore. You know, it used to be that people would invite me to give a lecture on exotic dark matter models, and now I get invited to give lectures about ordinary dark matter models. And it's not because I've changed, it's because our perceptions about models have changed. And so I really want to emphasize that because there's a lot of built-in institutional opinions about what makes a normal or nice or good model of dark matter. And I really want to emphasize, where we started, I'm going to end here. Nobody knows what they're talking about. If you have a model that looks interesting to you, you should work on it. Don't listen to anybody like me saying like, I don't like it. Because that's just based on what I'm used to and what I've spent my time doing. You should totally ignore people like me when we give you bad attitudes, and you should work on it, because there's it's a huge space of models and signals, and so I think there's a lot of fun to be had in it. So I will stop there. Thank you.